Arrival of raw materials. The first step in the manufacturing process is the arrival of raw materials, which are usually in the form of billets, bars, or ingots. Sawing and heating. Once the raw materials are inspected and approved, they undergo sawing to cut them into manageable sizes. This step is essential to prepare the material for the next phase, which involves heating. The sawn pieces are then heated in a furnace to reach the necessary temperature for forging. The heating process is crucial as it softens the metal, making it malleable and easier to shape in subsequent forging steps. Upsetting and setting down. After the material has been sufficiently heated, it is subjected to upsetting, where the material is compressed to increase its cross-sectional area. This step is followed by setting down, which helps shape the material into the desired form. Upsetting and setting down are essential for preparing the material for solid forging, as they allow the metal to be better shaped under pressure. Solid forging, cogging, and scarfing. Solid forging is a fundamental process that involves applying high pressure to shape the metal into the required form. This is achieved by hammering or pressing the material into dies or molds. In some cases, cogging is used, where the material is reduced in thickness and length through repeated forging processes. During this stage, scarfing may be required to remove any surface imperfections, such as oxides or scale, ensuring the metal's surface is smooth and ready for the next phase. Adding coal as a lubricant and turning around. To facilitate smoother forging and prevent frictional damage, coal is sometimes added as a lubricant. Hollow forging and expanding. Hollow forging is employed when the product requires a hollow or cylindrical shape, such as pipes or rings. This process involves creating a hole in the center of the material and then expanding it to the desired size. Straw boss, tap forging, and straightening. In some cases, a straw boss or a skilled supervisor is involved in monitoring the process, ensuring that each step is carried out to perfection. Tap forging is another method used to shape the material, where repeated taps with a hammer or press help refine the shape. Straightening is necessary after forging to correct any warping or bending that may occur due to the intense pressure applied during the forging process. Cutting and marking. After the forging process is complete, the product is cut into the required size and shape. This step is followed by marking, where identifiers such as serial numbers, product codes, or quality control stamps are added to the component. These markings help track the product throughout the manufacturing process and provide essential information for quality control and traceability. Heat treatment, normalizing, tempering, and quenching. Once the forging and machining processes are complete, the product undergoes heat treatment to enhance its mechanical properties. Normalizing is the first step, where the material is heated to a specific temperature and then air-cooled to improve its microstructure. Tempering is done next to reduce brittleness and increase toughness by reheating the material to a lower temperature and cooling it slowly. Finally, quenching involves heating the material to a high temperature and then rapidly cooling it in water or oil to harden the steel. This step increases the material's strength and durability. Grinding, run-out measurement, and inspection. After heat treatment, the product undergoes grinding to remove any surface imperfections and achieve the desired finish. Run-out measurement is performed to check the roundness and accuracy of the component. Rigorous inspection follows, including dimension measurement and testing for defects using methods like magnetic particle testing and ultrasonic testing. These tests ensure that the component is free from cracks, voids, or other imperfections. Material and tensile testing, impact testing. Material testing, including tensile testing, ensures the product meets strength requirements by evaluating its ability to withstand tension without breaking. Impact testing is also conducted to determine the product's resistance to sudden shocks or impacts, which is especially important in industries such as aerospace and automotive manufacturing. Rust prevention, shipping, and partner collaboration. To protect the final product, rust prevention measures are applied to prevent corrosion during storage and transportation. Once these measures are in place, the product is ready for shipping to customers. Lathe machining and five-faces machining. Lathe machining and machining centers are used for precision shaping and finishing of the product. The product is rotated on a lathe while a cutting tool shapes it into the desired form. In some cases, five-faces machining is utilized, where multiple sides of the component are machined simultaneously to improve efficiency and precision. The five-axis machining process represents a breakthrough in precision manufacturing, enabling the creation of complex geometries with unparalleled accuracy. Starting with a 120-kilogram block of A7N01 aluminum, the final product weighed just 3.6 kilograms, showcasing the precision of material removal. The machine, equipped with a 500mm table, allows for nearly spherical objects to be machined by processing all areas except the clamping points. Utilizing advanced CAM software, such as HyperMill, ensures the machine operates with exceptional precision, avoiding tool interference and maintaining efficiency. The project utilized a DMG 5-axis machine, renowned for its reliability and accuracy, even at a time when such technology was still developing. By leveraging the combined expertise of engineers, cutting-edge programming algorithms, and innovative machinery, the project set a benchmark in 5-axis machining. The result is a meticulously crafted helmet that continues to symbolize the potential of advanced manufacturing. The casting process at this factory is a highly organized and precise manufacturing operation designed to produce high-quality components for various industries. It involves transforming raw materials into finished parts using advanced technologies and efficient workflows. Design and mold preparation. The process begins with product design using advanced simulation software to optimize mold and gating systems. Expert teams create molds, often made of sand or metal, tailored to meet specific customer requirements. At the factory, molds are assembled and tested for accuracy, ensuring they are ready to handle the casting process. Melting and pouring. High-capacity electric furnaces melt metals such as steel, aluminum, or copper alloys. At precise temperatures, the molten metal is poured into the molds. Automated handling systems ensure uniform pouring, reducing defects and improving efficiency. Solidification and cooling. After pouring, the molten metal solidifies within the mold. The factory employs cooling technologies and monitoring systems to control the cooling rate, which is crucial for achieving the desired mechanical properties in the final product. Demolding and cleaning. Once the casting solidifies, it is removed from the mold using specialized equipment. The cast parts are cleaned, and any extra material, like runners or gates, is trimmed. Vibratory and abrasive cleaning systems may be used to achieve a smooth surface finish. Post-processing and quality control. The cast components undergo finishing processes such as heat treatment, machining, painting, and coating. The production process of deep groove ball bearings is a precise and automated endeavor designed to ensure high-quality products that meet stringent industrial requirements. Cutting-edge, fully automated production lines form the backbone of the manufacturing process. The sequence starts with forging the bearing rings, followed by turning, heat treatment, and grinding operations to achieve the precise dimensions and smooth surfaces essential for optimal performance. Grinding is conducted with extreme accuracy to ensure tight tolerances and consistent quality. Once the bearing rings are prepared, they proceed to the assembly stage. In this phase, rolling elements, such as steel balls, are inserted into the rings alongside cages that maintain proper spacing and alignment. Different sealing variants, including rubber or metal seals, may be applied based on customer specifications to ensure the bearings can perform in diverse environments. Quality management is integral to the production process. Automated lines incorporate advanced quality control systems, including real-time monitoring and post-production testing. These systems ensure that every bearing meets international quality standards, delivering precision and reliability. The final stage involves packaging and shipping. With an annual production capacity exceeding 100 million units, companies like LFD serve as reliable partners for various industries, offering bearings that excel in precision, durability, and cost efficiency. Material expertise. The Foundry processes approximately 30,000 tons of raw material annually, offering a broad selection of ingot formats and cross-sections. Their specialization lies in high-grade construction steels, alloyed quenched and tempered steels, case-hardening steels, as well as corrosion, acid, and heat-resistant grades. Precision in cutting. Using more than 20 circular and band saws, Durostal cuts ingots and pre-forged long products like shafts, rods, and blocks with millimeter accuracy. Forging expertise. Once heated to 550 to 1250 degrees Celsius, the material undergoes forging. While the traditional hammer and anvil have been replaced by modern technology, the principles remain the same. Smaller pieces, weighing between 10 and 2,500 kilograms, are forged using steam hammers and hydraulic presses with capacities ranging from 300 to 6,000 kilograms. Larger pieces are manipulated under electro-hydraulic systems, allowing free-form forging of custom shapes and sizes in both single-piece and series production. Advanced pressing technology. For applications requiring larger workpieces, 2 hydraulic 4-column presses with capacities of up to 40,000 tons are utilized. This advanced pressing technology allows the production of extreme dimensions, including drive shafts and axles, in a single operation. Supported by rail and free-fall manipulators with up to 50 tons of lifting capacity, the presses ensure precise, cost-efficient results. Computerized process monitoring ensures precise dimensions, optimal material flow, and consistent quality. Rings up to 3,500 mm in outer diameter, 850 mm in height, 500 mm in wall thickness, and 8 tons in weight are produced. Ring rolling innovation. Pre-forged hollow discs serve as the starting material for seamless rolled rings. On 2 state-of-the-art ring rolling systems, these rings are shaped and densified for optimal properties. These rings are later used in gears, bearings, sealing rings, and various other applications. Heat treatment excellence. Through fire and flame, the workshop transforms forged workpieces into components with optimal properties via intensive, product-specific heat treatments. Employing advanced burner technology, they perform all common heat treatment processes, including hardening, tempering, and annealing, at temperatures up to 1,250 degrees Celsius. This step unlocks the hidden potential of forged steel, enhancing surface hardness, toughness, and wear resistance. Mechanical precision. On a 9,000 square meter workshop floor, approximately 130 employees meet customer requirements for mechanical turning and milling. High-precision CNC machines allow the production of complex workpiece contours with tight tolerances. Whether deep hole drilling up to 4,200 mm, milling, or turning large pieces up to 35 tons, Durostal delivers custom machining with unparalleled precision. China has made significant advancements in the field of large and complex part machining using CNC technology. With a growing number of highly skilled technicians, state-of-the-art machines, and a well-established supply chain, China has become one of the leading players in global CNC machining for large parts. CNC machining centers in China are equipped to handle large-scale components, with some machines capable of machining parts up to 80 meters, 262 feet, in length. These machines offer precision tolerances of up to 0.01 millimeters, ensuring the production of high-quality, complex parts across a variety of industries, including aerospace, shipbuilding, and energy. For example, large vertical CNC milling machines, such as the ones found in leading Chinese machining factories, are capable of processing parts weighing up to 100 tons. These machines use multi-axis technology, enabling the machining of intricate shapes and features with exceptional accuracy. With the ability to perform multiple operations like milling, drilling, and tapping in a single setup, these machines significantly reduce production time and increase efficiency. In the aerospace industry, China has developed specialized CNC machines to produce turbine blades, engine components, and airframe structures. These parts often require complex geometries and tight tolerances, which can be achieved through advanced CNC systems. Machines with 5-axis capability allow for the production of highly detailed, precision components with smooth surface finishes, meeting stringent safety and performance standards. In shipbuilding, CNC machines in China are utilized to manufacture large parts such as hull sections and propellers. The sheer size of some of the components, coupled with the complexity of their shapes, makes CNC machining an ideal solution for these applications. These machines also play a crucial role in producing parts for the energy sector, such as large-scale turbines and generators. China's CNC machining industry benefits from a combination of advanced technology, skilled labor, and competitive pricing, making it an attractive destination for companies looking to outsource large and complex part manufacturing. The country's ability to deliver precise, cost-effective solutions for large-scale projects continues to cement its position as a global leader in CNC machining. The axle production process involves a series of precise steps to ensure the final product meets stringent quality standards. It begins with axle forge, where the raw material is heated and shaped into an axle blank using a forging press. Next, the loading process involves placing the forged blanks onto the production line for further processing. The axle then undergoes end facing, where both ends are machined to ensure proper alignment and uniformity. This is followed by roughing, where the basic shape of the axle is refined through a series of rough machining operations. The axle is then subjected to finishing, which involves precision machining to achieve the final shape and dimensions. Cold rolling is next, where the axle undergoes a deformation process to enhance strength and improve dimensional accuracy. After rolling, the axle is subjected to grinding to remove any surface irregularities. The axle then undergoes grinding 2, a finer grinding operation to achieve smoothness and further refine the surface finish. The axle is then washed to remove any remaining debris or contaminants. A dimensional check ensures that the axle meets precise specifications. Additional magnetic testing may be performed to detect surface defects, followed by marking and labeling for identification. Finally, the axle is subjected to an ultrasonic test to check for internal flaws. Once all tests are passed, the finished axles are unloaded and ready for shipment, ensuring they meet the required standards for performance and safety. Massive forming plays a critical role in various industries and is indispensable in the production of vehicles. No car can function without components that have undergone massive forming processes. In passenger cars, These components are predominantly used in engines, transmissions, and chassis systems. They are responsible for transmitting forces and movements, enduring high dynamic loads, and ensuring absolute reliability. In Germany, approximately 63% of the production from massive forming is supplied to domestic buyers, while 37% is exported. The primary consumers include the automotive industry, its system suppliers, and the machinery manufacturing sector. These percentages reflect production volumes in tons. The leading methods used in massive forming include closed die forging, open die forging, rolled rings, flanges, pipe fittings, and cold extrusion. Germany is a global leader in the production of massively formed components, surpassed only by China due to its vast domestic demand. The statistics are based on production volumes measured in thousands of tons. The continuous development in massive forming ensures the functionality of vehicles, whether in engines, transmissions, or chassis systems. Components such as suspension parts are tested on dynamic test benches to assess their durability and properties. The superior characteristics of massively formed parts are evident not only in testing but also in practical applications. In commercial vehicles, numerous massively formed components reliably perform under heavy loads. For example, heavily stressed parts of truck engines and suspension systems are produced using massive forming techniques. Highlighted components in truck drivetrains and transmissions demonstrate the extensive use of this technology. Even in areas like trailer hitches and construction machinery, massively formed parts withstand extreme stresses over long periods. These components, such as the elements in crawler undercarriages or excavator teeth, are typically closed die forged to ensure durability. Massive forming is also critical in producing components for ship engines and stationary motors, which demand absolute operational reliability. Parts such as crankshafts, connecting rods, camshafts, rocker arms, valves, and fuel injectors are manufactured to meet stringent safety requirements. Steam turbines in power plants use forged shafts and turbine blades made from heat-resistant materials. Similarly, for railway vehicles, motor and drivetrain components, as well as critical safety parts like wheels, axles, and brake components, are massively formed. The aerospace industry relies heavily on massive forming for components subjected to extreme dynamic and thermal loads. Engine parts such as shafts, high-precision turbine blades, and landing gear components are forged from materials like steel, aluminum, or titanium. These components ensure performance and safety in demanding environments. Modern forging processes demonstrate the high level of automation and precision in massive forming. For instance, truck axle journals are produced by inductively heating steel billets to approximately 1,250 degrees Celsius. These billets are then cut into sections, preformed by robots, and subjected to forging in a series of presses. The final contour of the component is achieved using an 80 megaton eccentric press, equivalent to 8,000 tons of force. The subsequent trimming process removes technical flash, and controlled cooling ensures the desired mechanical properties without additional heat treatments. Transfer forging presses enable the automated production of symmetrical components in high volumes through multi-stage processes. In such presses, round material is heated to forging temperatures and then transformed into dimensionally accurate parts through multiple stages. Cold extrusion is another prominent method, particularly for producing rotationally symmetrical components with high precision. Horizontal cold formers operate at high speeds, producing accurate parts with minimal finishing required. These machines are ideal for high-volume production, such as starter motor shafts or intricately shaped components like excavator teeth. Hammer forging remains a key method for producing parts such as car crankshafts and other structural components. Heated billets are transported to forging hammers, where preforming and final forging occur. Trimming and post-processing steps, like calibration, ensure the final dimensions and properties of the parts. Ring rolling is a specialized technique used to produce seamless rings. A pre-forged and pierced disc is placed in a rolling mill, where it undergoes radial and axial deformation to achieve the desired dimensions. This method is cost-effective for medium to large production volumes and eliminates the need for trimming. Similarly, cross-wedge rolling is used to form components like shafts by shaping heated billets between profiled rollers. The seamless steel pipe manufacturing process involves several advanced stages to ensure precision and quality. Initially, billets are heated uniformly in an annular furnace to achieve the required malleability. Next, the heated billets undergo piercing to create a hollow shell, a critical step that determines the pipe's initial dimensions. This shell is elongated and shaped in the pipe mill to achieve the desired diameter and thickness. Further fine-tuning is conducted at the sizing mill to refine dimensions and enhance surface quality. The pipes are then cooled, followed by sawing to cut them to specified lengths. Afterward, straightening ensures alignment and shape uniformity. Quality checks include a visual inspection and non-destructive testing to detect internal or surface defects. Finally, pipes are marking with specifications, racking for secure packaging, and prepared for shipment in sizes like 273 x 8 mm, 139.7 x 7.72 mm, and more. Steel long products are a vital segment of Arium's operations, centered around the integrated production at the Whyalla Steelworks. This facility showcases a seamless journey from raw materials to finished products tailored for construction, rail, and other industries. The process begins with iron making, where hematite iron ore from Arium's nearby mining operations at Middleback Ranges is utilized. Approximately 1 million tons of coal are processed annually in the coke ovens to produce coke, the primary fuel for the blast furnace. Inside the furnace, coke, iron ore in lump and pellet forms, and fluxes are combined with superheated air to create molten iron. The molten iron is then transported to the steelmaking department, where it undergoes refinement in the basic oxygen steelmaking (BOS) plant. Here, carbon and silica levels are reduced to produce various steel grades. The steel is then directed to one of two casting facilities: the billet caster, capable of producing 750,000 tons of billet steel annually. The continuous slab and bloom caster, producing 300,000 tons of slabs for structural sections and 100,000 tons for rail sections. Once solidified through water cooling, the bills, slabs, and blooms are sent for further processing. At the rolling mills, they are shaped into long products, including rails, structural sections, and reinforcing steel. The Whyalla facility is uniquely positioned as Australia's sole manufacturer of rails, serving critical construction and transport sectors. For East Coast operations, bills are transported for value-added processing, producing products for automotive, mining, and reinforcing applications. The steelworks' capacity and versatility allows it to contribute to landmark projects like the Adelaide-Darwin Railway, Melbourne Convention Centre, and Perth Arena. In addition to production, Arium emphasizes safety, environmental stewardship, and community engagement. These core values guide its operations, fostering sustainability and mutual growth with the local Whyalla community, which the steelworks has supported since its inception in the 1940s. This steel mill stands as a leader in forging technology, offering an extensive fleet of advanced machinery for high-performance manufacturing. Specializing in forgings with a maximum weight of 50 tons, the steel mill boasts impressive press capacities of 3,200 and 6,000 tons, ensuring efficient and precise production. The mill is equipped with state-of-the-art heat treatment capabilities, enabling it to achieve the highest quality standards in its products. Innovation is at the heart, with a fully computerized control system driving operations. This system ensures precision and consistency across all stages of production. The steel mill excels in machining, delivering high-quality precision finish machining to meet the most demanding specifications. To guarantee product integrity and performance, the steel mill employs ultrasonic devices for advanced quality control, detecting potential material imperfections that could impact the final product's reliability. The mill operates a highly efficient warehouse, supporting global operations and enabling prompt worldwide shipments. Lucchini RS's new rolling mill is designed for integrated production, eliminating the need for intermediate warehousing and improving operational efficiency. The facility features a rotating furnace with a 23-meter diameter, capable of processing 40 tons per hour, ensuring a steady supply of material for production. Two powerful hydraulic presses, with capacities of 9,000 tons and 5,000 tons, are employed to shape and form the wheels with high precision. The production rate is impressive, with the mill able to manufacture up to one railway wheel every 58 seconds. The rolling machine is equipped with 13 computer-controlled axes, allowing for highly accurate and flexible shaping of wheels. This advanced control system ensures that wheel dimensions range up to 1,450 millimeters, meeting the needs of various railway systems. Additionally, the new railway wheels heat treatment line is integrated into the process, ensuring that the wheels undergo the necessary thermal treatments for enhanced durability and performance. Ring rolling and close die forging are key manufacturing processes used to create high-quality metal components with precise dimensions and excellent mechanical properties. Ring rolling is a process where a metal billet is passed through rollers to form seamless rings. This technique is used for producing large, critical, and complex parts such as turbine rings, flanges, and bearing races. The process can work with a variety of materials, including carbon steel, low and high alloy steel, precipitation-hardened steel, stainless steel, and non-ferrous metals. It is highly customizable to meet the specific profile and size requirements of each part. Close die forging involves shaping a heated metal billet by applying high pressure within a closed die. This process is particularly effective for creating parts with intricate shapes and superior mechanical properties. It is commonly used for manufacturing components in sectors such as aerospace and heavy machinery. Both processes are supported by advanced in-house facilities, including a heat treatment plant for normalizing, hardening, and quenching, ensuring the components meet required standards for strength and durability. Additionally, CNC and VMC machines are utilized for precise machining and finishing, ensuring tight tolerances and high-quality results. The foundry industry in India is one of the largest and most significant sectors in the country, playing a crucial role in supporting key industries such as automotive, railways, defense, aerospace, construction, and agriculture. With over 4,500 foundries, India is the second largest producer of castings globally, following China. The industry employs approximately 500,000 people directly and indirectly, making it a vital contributor to the nation's economy. Production capacity and exports. India's annual casting production capacity stands at around 12 million metric tons, with current output levels hovering close to 11 million metric tons per year. The industry produces a wide variety of castings, including ferrous, gray iron, ductile iron, and steel, and non-ferrous, aluminum, brass, and copper alloys. Approximately 15 to 20% of the total production is exported to countries such as the United States, Europe, and the Middle East, contributing over $3 billion in export revenue annually. Key segments and demand drivers. Automotive sector. About 40% of the castings are consumed by the automotive industry, which includes engine blocks, brake drums, crankshafts, and gearboxes. Agriculture and construction. These sectors account for 25 to 30% of the demand, driven by components like pumps, valves, and heavy machinery. Railways and general engineering. The remaining 30 to 35% is used in railways, defense, and infrastructure projects. Challenges and opportunities. While the foundry industry in India has achieved significant milestones, it faces challenges like high energy costs, environmental compliance, and a lack of skilled manpower. Energy costs alone constitute about 20 to 25% of the total production cost, posing a hurdle to competitiveness. Additionally, adherence to global sustainability norms and environmental regulations is becoming increasingly critical. On the upside, the government's initiatives like Make in India and infrastructure development projects are expected to drive domestic demand. Moreover, a growing shift toward lightweight and precision casting, particularly for electric vehicles and aerospace, presents new growth opportunities.